Hi, in this video I'm going to explain certain formal properties of topological Hochschild homology. For example, we will have several base change formulas relating topological Hochschild homology relative to the sphere and relative to different bases like Hochschild homology. We'll also see that topological Hochschild homology of commutative ring spectra has a universal property, and as an application of that base change technology, we will prove a relative version of Berkshire periodicity for perfect FP algebras in place of FP. Hi, I'm Thomas Nikolaus from Mathematik Münster. And in order to talk about properties of THH, let's quickly recall what THH was and what kind of object it had as an input. And the object that we had as an input was an algebra in the infinity category of spectra. And recall that algebra means associative algebra, which is, as we've seen, equivalent to E1 algebras. And of course, the point is that this category has as a full subcategory the category of algebras in abelian groups, which is just the ordinary category of associative rings. And the inclusion takes an abelian group to its associated Eilenberg-MacLane spectrum. And we will sometimes, so this sends an abelian group or a ring to the Eilenberg-MacLane spectrum HR, and sometimes for convenience we will drop the letter H and just refer to it as R, especially if we do that in the context of THH. So for such an E1 algebra we have THHR, and that was defined to be the colimit of the cyclic bar construction. So the colimit over delta op of the diagram can be written like this, and here the tensor product is the tensor product of spectra, which we sometimes for clarity write as tensor over the sphere. And that is just going to be a spectrum. And again, if R is an ordinary ring, then we will drop the letter H in here, so to avoid awkward notation in language. And if R is a K algebra, where K itself is a commutative ring spectrum. For example, K itself is an ordinary commutative ring, like the integers. Then we also have THH R relative to K, which is just the colimit over delta op of the relative cyclic bar construction. So you do just your tensor over K. Or maybe in the notation that we've introduced, this is a little bit more canonically, it's Hochschild homology of the algebra R relative to the infinity category of K modules, which is a symmetric monoidal infinity category. So a K algebra, in other words, is the same as a commutative algebra. If R is a K algebra, so R is, in other words, a commutative algebra in the symmetric monoidal infinity category of K algebras. Okay, then we have this relative Hochschild homology. And a specific case of that, a specific instance, is ordinary Hochschild homology of R, which we defined in, this is relative to the integer, which we defined to be the cyclic bar construction in the derived category. This is now equivalent to THH R relative to the integers, which is then the colimit over delta op of the cyclic bar construction R, where then we have R tensor Z R. And that makes sense as soon as R is a Z algebra, for example, if R is an ordinary ring. And that relies on the fact that as symmetric monoidal infinity categories, the derived category is equivalent to the category of HZ modules in spectra. Okay, so that is what we have about topological Hochschild homology, this relative topological Hochschild homology. And now the first statement I want to make today about formal properties of THH, the following proposition. This is that THH, this is a functor which takes an associative algebra in spectra and produces spectrum, or more generally, this is a symmetric monoidal functor. Monoidal functor. And by symmetric monoidal, I mean strong symmetric monoidal functor. And what are the symmetric monoidal structures in question here? Here the symmetric monoidal structure is a pointwise tensor product. So the tensor product of two algebras is just the tensor product. So in other words, in particular I claim that THH A tensor B for two algebras, A tensor over the sphere B is again an algebra, and the claim is that THH of that is just THH A tensored over the sphere with THH B. And more generally, we have Hochschild homology blank relative C, which goes from algebras in any symmetric monoidal infinity category C to C, provided that C has the necessary geometric realizations for this to exist, is symmetric monoidal. Okay, that is the statement. So it's a symmetric monoidal functor. And how do we see that? And as a first thing, it's maybe a good exercise, without giving that as a formal exercise here, to check that this formula holds true, that we have an equivalence between those two guys. And this just follows by expanding what that is in terms of the cyclic bar construction. You get A tensor B, A tensor B, tensor A tensor B, and so on. And convincing yourself that the cyclic bar construction of A tensor B is just a tensor product, a pointwise tensor product of the cyclic bar constructions. And then you use that geometric realizations interact well with tensor products. So this way you can directly prove this formula by hand. But of course, being a symmetric monoidal functor is a more refined statement than just this equivalence. It's kind of a coherent version of this equivalence. And one way to see that this is actually true, and let me do that in the case THH, the general case works exactly the same, is by consider the functor, the forgetful functor from algebras in spectra to spectra as an object in the symmetric monoidal infinity category, monoidal infinity category of functors from alg spectra to spectra. Right? This category is symmetric monoidal by means of pointwise tensor product. Just a functor category, and I give it the pointwise tensor product. And U is a object, but in fact it's an algebra. Is an algebra in there. And this is just, if you think about it, think about what it means to give this the structure of an algebra object in this functor category, you'll see that this is exactly a refinement of the forgetful functor through the category of algebras. Or maybe at least it follows from that. And then you see that this is obviously given. So, and then THH as a functor is just Hochschild homology of that functor U relative to this functor category. Okay, so that was now a very complicated way of saying that THH is a functor. But the point is, now we observe that by construction of the pointwise tensor product on algebra of spectra, this is in fact a functor in symmetric monoidal functors from algebra spectra to spectra, and it's an algebra in there. And so I can just take this construction. And the point is that the necessary colimit, which is the geometric realization, exists as a functor in here. And if you think about what I've done, I'm just using that all the tensor products and geometric realizations are just pointwise. And that, if you do it correctly, provides the correct proof. So it's maybe, this looks a little bit like cheating, but if you think it through, this is a correct proof. Once you believe or prove the statement that this is in fact an algebra in symmetric monoidal functors, and you use the fact that geometric realizations of these symmetric monoidal functors exist and are computed underlying. And what's the significance of the last statement? The significance is, for example, the following. Corollary, if R is En, is an EN ring spectrum, or is an EN ring spectrum, I will probably most of the time just say R is EN, then THH is canonically, and I'm dropping the word canonically, is EN minus 1. So I should maybe more generally say canonically inherits the structure, or naturally inherits the structure of an EN minus 1 ring spectrum. In particular, if n is equals 1, then I'm just saying this is E0. This is a pointed object, which is just a map from R to THHR, coming from the bottom cell of the cyclic bar construction. But for other n, this is a non-trivial statement. And the proof is the following. I guess it follows from what I've done before. EN algebras in spectra are by Dunn additivity the same as EN minus 1 algebras in E1 algebras in spectra. And now I can just apply the functor THH. So THH, in fact, I should have said this here, THH only depends on the underlying E1 structure of the EN ring. And so I'm just applying ALCH EN minus 1 to THH, so that I land in EN minus 1 of spectra. And so I'm just post-composing with a symmetric monoidal functor and use that algebras, maybe I should write this as ALCH EN minus 1 applied to THH. So I'm just observing that symmetric monoidal functors preserve algebra objects. Okay, so that proves this claim, which is an important claim. So applying THH loses one layer of commutativity. It's maybe the upshot. And in particular, we have something which we've already seen. Achim has already used this, that for n equals infinity, we have that that THH is also E infinity, so it's commutative. We can deduce that from this formula, but in fact, actually something much stronger is true. For E infinity ring spectra, we can describe THH a little bit more canonically. And for this, recall the following fact. If A and B are, and by the way, everything I'm going to say here about THH is generally true about Hochschild homology in the general symmetric monoidal infinity category, but I think this would only add notational complexity to what I'm doing here. So let me do it for THH. So if A and B are commutative algebras in spectra, in other words, E infinity ring spectra, then I can form A tensor B. And this is just a pointwise tensor product. For every EN algebra, this would again be an EN algebra, but the point is that this is a coproduct in commutative algebras in spectra, right? This is an incarnation of the fact that in ordinary commutative rings, the tensor product is a coproduct which completely fails in associative rings. And here it fails for EN rings for n less than infinity. Okay, so here's a statement about what this is. THH for E infinity rings, and it is for R, a commutative algebra in spectra. We have that THHR is actually the colimit over the space S1. So homotopy type S1 over the constant diagram with values R. Right? Let me just denote this as R. By this I just mean the constant diagram with values in R, and that is in the category of commutative algebras in spectra. So this is a diagram which goes from S1 to the point and then into the category of commutative algebras in spectra, where I just put R here. This is the map determined by R, and this is the projection. So that's a constant diagram with value in R, and I will write this as R to the tensor S1. for this colimit of the constant diagram. So recall earlier at some point we had used the notation that a colimit over a constant diagram would be written R tensor S1, but here I'm going to write it R upper tensor S1. Why is that? Because in this case, if A is equal B, then A tensor S A is also the colimit over the constant diagram of the set with two elements, 0 and 1, of the constant diagram A, right? And this I want to, of course, write as A tensor 2. And it would start look a little funky if I don't write it like this. Okay, and again, more generally, this is true in every symmetric monoidal infinity category, that Hochschild homology in that symmetric monoidal infinity category is a colimit over S1 of commutative algebras, under the assumption that all the colimits exist. And this I want to leave as an exercise. So the exercise is to prove that THH is this colimit. And there are basically two ways of solving this exercise. The first way would be to take this formula and write down, you use a cell decomposition of S1. There's a description of S1 as a simplicial object which has a single n cell in every, possibly degenerate, but has exactly n plus 1 n simplices. And if you use this formula and you expand out and use the fact that the tensor product is a coproduct, you literally get the cyclic bar construction. Another way of solving this exercise is to use the formula that THH R is R tensored over R tensor R op with R. And again, you can use this and write it as a certain push out in commutative algebras to see that this formula is true. Okay, that is the exercise here. And let me maybe write out the warning that I basically already issued, but the warning is the following. This colimit, column in the category of commutative algebras in spectra, usually I don't denote this colimit, but let me write it here, over R is different from the colimit column over the constant diagram with values R in spectra. Right, if I don't compute the colimit in commutative ring spectra, but just in spectra. And that latter colimit, which is given by, I guess again you can compute this in terms of, for example, if you did the last exercise, there's a similar formula. This latter here you would take the coproduct in R tensor R, and you would end up having this coproduct, and then it would be the colimit over delta op. So this is equivalent to that. If you expand out this diagram, another way of writing that is R tensor S1. You just tensor with the space S1, or this might actually mean R tensors the suspension spectrum of S1, and then you see that this is actually, this colimit is additive colimit is R plus sigma R. Just a copy of R and a shifted copy of R. And that is much easier. And please be aware, some sources in the literature use this formula R tensor S1 to denote this colimit in the category of commutative algebras, which I prefer to write R upper tensor S1 to distinguish it from the underlying additive colimit. But of course, I guess that one way or the other, you have to somehow say in which category you compute a colimit, and you want to maybe make clear that there's no confusion. Okay, so that was my warning. And now, after having proved this formal property, I want to deduce some or prove some base change formulas. So this formal property about THH of E infinity rings will come very handy later on. But let me first prove some base change formulas. Base change formulas for THH. we've already seen that, I mean, THH of a tensor product is THHA tensored over S THHB. And what I will want to prove now are formulas where you also take a tensor product of THH. And we will deduce those from more general formulas. And so the first statement is for any lag symmetric monoidal functor, C to D, F, between symmetric monoidal infinity categories. So C and D are symmetric monoidal infinity categories. F is a lag symmetric monoidal functor. We get a canonical map. I should maybe say natural, but let me say canonical from THH. I mean, A is going to be an algebra in C. So, and maybe I should write A is an algebra in C. And then I can apply F to A. And here I'm using a fact which, strictly speaking, we haven't introduced. But what is true is if you have an algebra in a symmetric monoidal category and apply a symmetric monoidal functor, lag symmetric monoidal functor to it, then the image is again an algebra. If you define an algebra as we did as a functor out of, I mean, fin S tensor active, then this is not immediate because, I mean, this is a symmetric monoidal functor and you can't just post-compose symmetric monoidal functor with lag symmetric monoidal functors to get another symmetric monoidal functor, but then you have to work a little bit. But it's a true fact, and I think you might know this fact from ordinary category theory, that you have this fact that this is a algebra again in the category D. And so we can take the, and I guess I want to write Hochschild homology in the symmetric monoidal infinity category D of FA. And the claim is that there's a canonical map into this from F applied to the Hochschild homology of A in the symmetric monoidal infinity category C. Okay, so that's a statement that there's such a canonical map. And if F is strong symmetric monoidal and preserves geometric relations, then this is an equivalence. Okay, and the proof is just, I mean, given that I haven't really gone through how FA precisely is an algebra, let me just tell you how this informally works and leave the details to be worked out by a very careful person. I guess, I mean, this can be found in the literature, by the way. And so what do we have to compare? So what we have to compare is F of the colimit of the cyclic bar construction in C, which would look like a tensor. This is a tensor product in C, and so on. And we would have to compare this to the colimit over delta of the cyclic bar construction FA tensor over in D, FA, sorry, this D is probably not readable at all. And then I have 3 copies of FA and so on. So we would have to compare these two guys. And of course, now the thing is that, I mean, being symmetric monoidal, I mean, I always get a map from the colimit here into the thing where I pull the colimit into F. Right, so I guess maybe I should write it here. I get a map from the thing where I have the colimit delta op of f of this diagram, f of a, then I have f of a tensor ca, and bracket it like this. Right, this is just the universal property of the colimit. For every functor you get a canonical map from the colimit of this functor applied to the diagram to as f of the colimit of the diagram. This is just coming from the fact that it's a colimit. And then being lag symmetric monoidal, I also get a map from here, fa tensor over dfa, into this guy. So a map like this. And I apologize for the confusing board work, but now of course the composite of these two maps is the canonical map that we care about. And this proves part one, except that we haven't really fully been rigorous about why this is a map of simplicial objects. But for the second part, you see that once f commutes with this colimit, this map is an equivalence, and if it's strong symmetric monoidal, this map is an equivalence. So that implies part two. Okay, and let me give you two examples of this general statement. So the first example is you consider the Eilenberg-MacLane spectrum functor from the derived category of C into spectra. And this functor is actually lag symmetric monoidal. And, well, this functor does preserve colimits, but we will not need that for now. And the point is, I mean, there's a bunch of ways of seeing that. One way is to observe that last time we argued that dz is in fact equivalent to modules over hz. And then there's a tensor product relative to hc and the tensor product relative to the sphere. And so the forgetful functor is lag symmetric monoidal. Okay, so now we can apply that. So what we get for an algebra in dz, for example, for an ordinary ring, we get a map, applying this observation there, we get a map from the Eilenberg-MacLane spectrum functor of the Hochschild homology of R relative Z. So that was a priori defined to be a chain complex, an object in the derived category. We apply the Eilenberg-MacLane spectrum functor to get a spectrum. And then we get a map from THH into this guy. I guess now I realize that I wrote the direction of the morphism wrong here. Sorry for that. Right, so here we get a morphism into this direction from THH R. And I really, strictly speaking, would have to write THH HR and not this. And this is a map that was already employed when we talked about Berkshire periodicity. On homotopy group, this gives a map from THH star R to HH star R. And we have seen that this map is in fact an isomorphism in degrees 0, 1, and 2, if R is an ordinary ring. That's the first example. What's the second example? It is a statement that if we have a map K to K prime, map of commutative ring spectra, so K is just going to be my generic letter for a base ring spectrum. Then we get the induced functor, which is induction, going from mod K to mod K prime of ring spectra. For example, if these are ordinary rings, then this is just the base change functor, the derived base change functor from the derived category of K to the derived category of K prime. And we get, now this functor is symmetric monoidal and preserves all colimits. In particular, it preserves geometric realization. So we get that THH of any k algebra R relative k if we tensor that with k to k prime. So that's applying the functor to THH. That is equivalent to THH of, and now I base change the R tensor k prime relative k prime. And that's a very, very important first base change formula. Just an application of our general result. Okay, and as an application of this base change formula, I want to prove an extension of Berkshire periodicity. So recall Berkshire periodicity was the theorem that THH of Fp was Fp adjoint x for x generator in degree 2. And now we want to prove a version for perfect rings. And for this, recall that an Fp algebra, a commutative Fp algebra, and by this I just mean an ordinary land. K, just an ordinary Fp algebra, no ring spectrum or anything. Commutative Fp algebra K is called perfect if the Frobenius endomorphism phi from k to k, which sends little k to the p, because we are characteristic p, this is a ring homomorphism, is an isomorphism. And of course k, the letter k is not supposed to suggest that this is necessarily field, but examples include finite fields Fp to the n, which of course this is in this case phi is a homomorphism of fields, hence injective, and thus for cardinality reasons also surjective. So finite field is a perfect Fp algebra, which is in fact why we denote this by k, but there are also examples which are not fields. For example, a ring like Fp adjoint x to the 1 over p infinity. Perfect Fp algebra, and by this I just mean you adjoin all the p's roots to x, or in other words, you take the colimit of Fpx over the Frobenius. This colimit. And I guess this is just a colimit in ordinary commutative rings, and you can just do that trick for every commutative ring. This is called the for every commutative Fp algebra, that's called the colimit perfection. Anyways, that's another important example of a perfect ring. And what we want to do is we want to, for a general perfect ring, compute THH and prove a version of Berkshire periodicity. And for such a perfect ring K, we have maps. I guess we have these maps more generally, but we have a map from HK, the Einberg-MacLane spectrum on K into THH K. So this is just because THH was a colimit which started with HK. So on homotopy groups, this gives me a map from K into THH star K, which in fact is an iso in degree 0, right? We know that this bottom cell map is just an iso to THH 0. And we also have a map from THH Fp into THH K, map of commutative ring spectra. And this just comes from the fact that it's characteristic P. So we have a map from Fp into K. And this on homotopy groups gives me a map from Fp adjoint X into THH star K. And of course we can combine those two maps together because they agree when we restrict to HFP, essentially by construction if you think about it. So we get a combined map using that THHK is a commutative ring spectrum from HK tensored over HFP with THHFP into THHK. And what does this map do on homotopy groups? And this I want to leave as an exercise. The claim is that on homotopy groups, this gives me a map from K adjoint X into THH star K, which in degree 0 sends K to K is an isomorphism, and in degree 2 sends this X to the image of the Berkshire element coming from THHFP. Okay, and the theorem is that we refer to as Berkshire periodicity. I mean, this is a name I think it was advocated by Lars Hesselholt. Berkshire periodicity for perfect rings states that for every perfect FP algebra, K, the map Kx into THH star K is an isomorphism of commutative rings. So in other words, THH of a perfect FP algebra is also just a polynomial ring on a degree 2 generator. Or equivalently, of course, I mean, this is just the effect on homotopy groups of this map. So equivalently, I could say this map is an equivalence. But using that this we had already identified as a free E1 algebra, you can also write this as saying that THHK is the free E1 algebra on X over K. Okay, and I want to prove this result now. The proof will use a certain fact, namely we use that for K perfect there is a commutative ring spectrum SWK called spherical bit vectors such that if I take these spherical bit vectors, which is a commutative ring spectrum, so it lives over the sphere, and if I base change it along the sphere to HFP, right, there's a canonical map of ring spectra from the sphere to HZ, just a projection to pi naught, and then go further down to HFP, and I base change along this map. And this resulting thing is a ring spectrum, and it's equivalent to HWK. And in fact, it's an FP algebra, it's just the FP algebra, sorry, not HWK, but just K. So said it differently, it's a lift of K along the map from the sphere to HFP. Right, generally, if you have a map of rings, it makes sense to ask for a lift of an algebra for the target over the source, and the same you can do for ring spectra. And the claim is there is such a map, and we will talk about these spherical bit vectors in a separate video. So these are constructed analogously using obstruction theory, analogously to the bit vectors were constructed, which we did in a video about the digression video about the cotangent complex. And similar tools here will give us this, and if I additionally put some properties like p-completeness, then this is even going to be a unique lift. Anyway, so I'm going to use that it lifts to the sphere. So what does this buy us? Now we want to compute THH of K. which is by definition THH k relative to the sphere. But this is now, by what I've written here, the same as spherical width vectors k tensored over the sphere with h of p. And then, by the fact that THH was symmetric monoidal, this is the same as THH of the spherical width vectors k tensored over the sphere with THH of h of p, I guess, but then we agreed to write this just as fp. And now, here comes the crucial trick. The right-hand side is an fp algebra. Or actually, for what I'm going to do, it's enough to say that this is an fp module, but I want everything multiplicatively, so I'm using it's an fp algebra. But then, whenever you tensor something with an fp algebra, can just sneak in another factor of fp. So you get that this is equivalent tensored over the sphere h of p, and then tensored over h of p with THH of p. Right, so I've sneaked in this factor of h of p, which cancels out. That's the general property of the tensor product. And I guess, strictly speaking, we haven't proven that, but it's proven similarly if you think about it, how this is defined as a bar construction, or you can also say it a little bit more formally to get this equivalence more coherently. But now we want to apply it to this term, our base change formula. So let me write that here. So this is just continuing from here. So the base change formula asserted that this guy is actually equivalent to THH of, and now I have to take the base change SWK tensored over HFP, which is just, by the formula upper here, it's K, relative to HFP. P, and then tensored over HFP with THH of P. And I guess I don't need a bracket here. And this is just Hochschild homology of K relative Fp. And because of this fact that this is just Hochschild homology, it suffices to prove that THH of K relative H of P, and I admit I'm a little bit inconsistent with where I put H's and where not, which is just Hochschild homology of K relative Fp, is isomorphic or equivalent to K, i.e., or maybe HK, i.e., HH star K relative Fp is 0 for star larger equal 1. Right? Because remember, in the end we wanted to prove that THHK is K tensor H of P, THH of P. And so in order to achieve that, it suffices to prove this. And this last claim I want to leave as an exercise. So to prove that HH star KFP is 0 for star larger equal 1, and this is a statement which is true for every perfect ring. And in order to do that, you should invoke the HKR filtration and use the fact that the cotangent complex of K relative Fp is 0. I don't want to say much more, but think about how the HKR filtration rises and how the cotangent complex helps me say something about that. Okay, and then this finishes the proof of Berkshire periodicity for perfect rings. And to conclude today's lecture, I want to give you one more base change formula for THH. And in order to do that, remember that if K is an E-infinity ring, then at the beginning of today's lecture we have proven that THHK is just given by K to the tensor as 1. Okay? And as a result, we get a map THHK down to K of E infinity rings, or commutative rings, as, I guess we use that THHK is just K upper tensor S1, or said differently, the colimit in commutative algebras in spectra of K over S1, and then we can project down from the map S1 to the point, right? And so we project down in the S1 variable to the colimit over the point in commutative algebras over K, which is just K. Or said differently, by the universal property of this colimit, writing down a map from K tensor S1 down to K amounts to giving a bunch of maps out of this diagram, or a natural transformation by the universal property of the colimit, and such a natural transformation is always just given by the constant map to K. Right? And this is the map of commutative ring spectra. And we get these maps, and such that the composite, if I go from K into THHK with the standard map, and down with this map we just have constructed, is the identity. And that is just by construction, because this map was just the inclusion of the zeroth layer into the colimit. And this map was constructed such that on each layer it's the identity. So in particular, this composite is the identity. Remark: such a retract does generally not exist if K is only En for n less than infinity. So for an associative ring spectrum, such a map does generally not exist. And this can be tested, in fact. If K is a ring spectrum, then of course this implies the fact that this retract exists, implies that this map is injective on homotopy groups. In fact, it splits off a factor summand of K from THHK, and you can prove that this can't be true in general. So that's something very specific. I guess you can also see that if you think about what this concretely means. I mean, you have to write down a natural transformation of this diagram into K, or into the constant diagram K. And that has to be compatible with the whole cyclic diagram, right? So what you of course want to do is you want to take the multiplication here, but generally the multiplication will not be a map of algebras anymore, so that this is not going to be compatible with this diagram. And if you start thinking about that, you also need that for higher layers, then I mean you can convince yourself that this is actually a very strong assertion. But anyways, for a commutative ring spectrum we have this map from THHK down to K, and the theorem is the following. And that is for if K is a commutative ring spectrum, and R is the K algebra, and associative K algebra, then I mean, and remember, a K algebra is just an algebra in the category of K modules, which makes sense because K was commutative. So the category of K modules has a symmetric monoidal structure, and then it makes sense to talk about associative K algebras. Then we have the formula. We can attempt to compute THH relative K. And the question is, what has this to do with the absolute THH of R? And the claim is that this is equivalent to THHR. So in other words, THHR relative to the sphere tensored over THHK. So that's the point. So there is now, by the fact that R is a K algebra and THH is symmetric monoidal, it follows that THHR is actually a module over THHK. Right? I mean, we lose one layer. It's not an algebra, but it's still a module, or an E0 algebra if you want, over THHK, which is a little bit more than a module. It also has a canonical map from THHK coming from the inclusion of K into R, or the functor map from K into R. And then we use this bottom cell map to base change this to K again. And this is a K algebra, right? Or a K module now. Take a THHK module and base change to K. And the claim is that this is equivalent to that. Okay, that is the last statement I want to make today. And in fact, there's also variants. I could put in a different base. Like if I have a base K and a base K prime, I can compute THHR relative K prime in terms of THHR relative K. I leave the details to the reader, but this is the absolute formula. So think this is THHR relative to the sphere. And let me just sketch the proof. And the sketch of proof is as follows. You just observe that what we have to compute in order to compute this term is the colimit over delta up of the term where I put R here, and then I have R tensor KR, and so on. And now the crucial observation is that we can rewrite the term R tensor over KR as the base change R tensor over the sphere R, base changed, and this is now a module over K tensor over the sphere K. K tensor over the sphere K to K. And similar for higher terms. So what I do is I write R tensor over KR as R tensor over the sphere R tensored over K tensor sphere K down to K. So that's a crucial observation, and the same for higher layers. And then the lower term is actually just the same, as you can write the whole diagram as the colimit over delta up of, and then I do the diagram where I do, I guess what's the best way of saying that? I mean, I just do the diagram where I have R. I guess I'm running out of spot space, so let me clean another board to say that a little bit better. So this whole thing I now want to write as a tensor product in diagrams, where I write this diagram, R tensor the sphere R, and so on, and tensor this over the diagram K tensor over the sphere K, and so on, with the constant diagram K, K, K. And all of these are diagrams, functors from delta up into spectra, and I consider this as an algebra in diagrams and these as modules over that. Right, so this is what this diagram is given, and then I should have actually, I guess, transferred this colimit also over. So the whole thing is the colimit over delta up of this tensor product of diagrams. And now we use the crucial fact that for geometric realizations, such a colimit is just the colimit of this guy tensored over the colimit of this guy and the colimit of this guy. This has to do with the fact that you can pull out geometric realizations out of tensor products, and not only in each variable separately, but diagonally. That is actually the crucial input about the category delta that you input here, so that you get that this is actually THHR tensored over THHK with K. Okay, and that finishes my sketch proof, and of course again I'm a little bit sloppy as in how coherently I've written down this equivalence and all these equivalences. But that should give you a pretty good idea of why this is true. Okay, this finishes my discussion of formal properties of THH for today. Thanks very much, and see you in the next video.